In digital electronics, an arithmetic logic unit is a digital circuit that performs integer arithmetic and logical operations. The ALU is a fundamental building block of the central processing unit of a computer, and even the simplest microprocessors contain one for purposes such as maintaining timers. The processors found inside modern CPUs and graphics processing units accommodate very powerful and very complex ALUs. A single component may contain a number of ALUs. Mathematician John von Neumann proposed the ALU concept in 1945, when he wrote a report on the foundations for a new computer called the EDVAC. Numerical systems. An ALU must process numbers using the same formats as the rest of the digital circuit. The format of modern processors is almost always the 2's complement binary number representation. Early computers used a wide variety of number systems, including 1's complement, 2's complement, sign magnitude format, and even true decimal systems, with various representation of the digits. The 1's complement and 2's complement number systems allow for subtraction to be accomplished by adding the negative of a number in a very simple way which negates the need for specialized circuits to do subtraction. However, calculating the negative and 2's complement requires adding a 1 to the low-order bit and propagating the carry. An alternative way to do 2's complement subtraction of or b is to present a 1 to the carry input of the adder and use a b rather than b as the second input. The arithmetic, logic and shift circuits introduced in previous sections can be combined into one ALU with common selection. Practical overview: most of a processor's operations are performed by one or more ALUs. An ALU loads data from input registers. Then an external control unit tells the ALU what operation to perform on that data, and then the ALU stores its result into an output register. The control unit is responsible for moving the processed data between these registers, ALU and memory. Complex operations: engineers can design an arithmetic logic unit to calculate most operations. The more complex the operation, the more expensive the ALU is, the more space it uses in the processor, and the more power it dissipates. Therefore, engineers compromise. They make the ALU powerful enough to make the processor fast, yet not so complex as to become prohibitive. For example, computing the square root of a number might use calculation in a single clock design, an extraordinarily complex ALU that calculates the square root of any number in a single step. Calculation pipeline design, a very complex ALU that calculates the square root of any number in several steps. The intermediate results go through a series of circuits arranged like a factory production line. The ALU can accept new numbers to calculate even before having finished the previous ones. The ALU can now produce numbers as fast as a single clock ALU, although the results start to flow out of the ALU only after an initial delay. Iterative calculation design, a complex ALU that calculates the square root through several steps. This usually relies on control from a complex control unit with built-in microcode. Coprocessor design, a simple ALU in the processor, and sell a separate specialized and costly processor that the customer can install just beside this one, and implements one of the options above. Software libraries tell the programmers that there is no coprocessor and there is no emulation, so they will have to write their own algorithms to calculate square roots by software. Software emulation emulate the existence of the coprocessor. Whenever a program attempts to perform the square root calculation, make the processor check if there is a coprocessor present and use it if there is one. If there is not one, interrupt the processing of the program and invoke the operating system to perform the square root calculation through some software algorithm. The options above go from the fastest and most expensive one to the slowest and least expensive one. Therefore, while even the simplest computer can calculate the most complicated formula, the simplest computers will usually take a long time doing that because of the several steps for calculating the formula. Powerful processors like the Intel Core and 64 Armenian DRAMs implement option number 1 for several simple operations, number 2 for the most common complex operations and number 3 for the extremely complex operations. Inputs and outputs. The inputs to the ALU are the data to be operated on and a code from the control unit indicating which operation to perform. Its outputs is the result of the computation. One thing designers must keep in mind is whether the ALU will operate on big-endian or little-endian numbers. In many designs, the ALU also takes or generates inputs or outputs a set of condition codes from or to a status register. These codes are used to indicate cases such as carry in or carry out, overflow, divide by zero, etc. A floating point unit also performs arithmetic operations between two values, but they do so for numbers in floating point representation, which is much more complicated than the 2's complement representation used in a typical ALU. In order to do these calculations, a FPU has several complex circuits built in, including some internal ALUs. In modern practice, engineers typically refer to the ALU as the circuit that performs integer arithmetic operations. Circuits that calculate more complex formats like floating point, complex numbers, etc. usually receive a more specific name such as floating point unit. See also, 7400 series, 74181, adder, multiplication ALU, digital circuit, division algorithm, control unit, central processing unit, bus, notes. References. Wang, Enoch. Digital Logic and Microprocessor Design with VHDL. Thompson. ISBN A0-534-46593-5. Stallings, William. Computer Organization and Architecture, Designing for Performance. Pearson Prentice Hall. ISBN A0-13-185644-8. External links, ALU and its micro-operations, Bitewise, Arithmetic and Shift, a simulator of complex ALU in MATLAB.